Okay, good. The first talk of today's session is Sergei Dubovsky. He will talk about Zigzag Model. Okay, please.
Okay. I don't know. Good evening. Good morning. For me, it's more like evening. Thank you for the invitation to speak. It was a bit hard to follow for the talks because of the time differences, but I saw some of them. And I will talk about well, this what we call zigzag model. And let me start with a bit of motivation and try and to explain how it's connected to the topic of the main topic of this conference, this workshop, namely TT-bar deformation. And it's going to be rather informal talk. As you see, it will be kind of blackboard talk. So please feel free to interrupt and ask questions. And I should say this work is being done in collaboration with Jack Donahue, who is a PhD student here at NYU. And there are two papers which I start with, which describe the classical dynamics of this model. And then I'll say about what we understood about quantum dynamics, and that's the work to appear, although there are still some puzzles there, which I'll explain. But let me start first with motivation. I should say, for me, the main motivation really is not coming from TT-bar side of the story. For me, TT-bar is more like a tool here. But my zero order motivation for this is that I'm interested in QCD strings. So this study was mostly motivated by this. But for folks here, let me present some motivations coming from TT-bar side. From TT-bar side of the story, the motivation can be formulated this way. So, well, TT-bar deformed theories are interesting non-local theories, which allow us to calculate at least two classes of observables. They allow to calculate S matrix, and they allow to calculate finite volume spectra. And looking at these observables, one finds immediately that they exhibit interesting and quite exotic UV behavior. In particular, there is no UV, even though these are UV complete series. In a sense, there is scattering amplitudes defined at all energies. They cannot be described in terms of the RG flow from UV fixed point to IR fixed points. There is no, the behavior at high energies is not conformal, and provides an example of a new kind of asymptotic behavior in quantum theory. Initially, we called it asymptotic fragility, but I may call it whatever one likes, but it's like interesting. Well, at least for me, that's the main interesting feature of these models. And there are two, for me, there are two closely related questions. One is, well, are there more theories of this kind? In particular, are there non-solvable examples? Are there non-solvable theories of this kind? So I should say already in TT-bar story, the theory in some sense not solvable, because you can start from any quantum field theory. It doesn't have to be integrable, and then this deformation exists. But the transition from the initial S matrix to deformed S matrix, that transition is relies on very special property of TT-bar operator, and that's given by exact formula. So in that sense, it's exactly solvable theory. And well, to claim that one really construct a large class of theories exhibiting new asymptotic behavior, I think it would be interesting to find examples where, well, which are more complicated, where one simple formula like this doesn't exist. Otherwise, it looks like more like very interesting, but isolated peculiarity rather than some new phenomenon, new class of theories. And the somewhat related question is what else can be calculated in this kind of series? What other observables can be defined in this series? Else can be calculated. And one reason these two questions are related is because in conventional quantum field theories, one can calculate, say, correlators of local operators. One can define local operators, and the moment one does that, that gives also a possibility to deform the theory. One basically starts with action of initial theory, and in the simplest case, just adds operators corresponding to relevant perturbations, and that defines new theory. So understanding answer to question 2 to some extent sheds light also on question 1. But for me, really kind of in what I will be talking about today, probably question 1 is the primary one. Now, the hint that there is the actual class of the theories which we're talking about is much larger than this exactly solvable example comes from thinking about already the very first and simple example of TT bar deformed theory, namely the theory on the wall sheet of critical strings. So the first example would be take 24 free massless bosons, TT bar deform them, and this way one gets the wall sheet theory of infinitely long bosonic critical string. String at G string equal to 0. So we're talking about here, we're not talking about space-time dynamics, we're talking about wall sheet dynamics, and that defines a unitary system at 0 string coupling constant. And there is a very simple geometrical reason why this happens. It's because TT bar phase, the famous TT bar phase shift, it corresponds to time delay proportional to the collision energy, and that's in some sense the most basic geometrical property of relativistic string, because when you have excitation on a relativistic string, the proper length of a string is proportional to the energy of the excitation, and that provides a geometric origin for this phase shift. So that's the simplest example. But that's also, this example suggests where else to look for more interesting theories of this kind. Namely, one needs to look at the wall sheet series of more interesting, more complicated strings. So critical strings, well, the special property is that the theory on the wall sheet is integrable there. However, well, we know that there are theories which give rise to wall sheet dynamics which is non-integrable, and large class of examples comes from thinking about dynamics of adjoint QCD like gauge theories. So it can be pure Yang-Mills, or can be pure Yang-Mills with some set of adjoint matter, such that center symmetry is not broken, and the theory has strings, infinitely long strings, which cannot be broken, and well, also the requirement that the theory should be in the confining phase, and that it should allow for conventional Tuft large NC limit. So, for instance, Seiberg-Witten theories don't satisfy this requirement because there, as one in the top limit, there is a proliferation of U1 factors, so they give rise to different dynamics. But there are still large class of theories which satisfy this requirement. Again, prototypical one is just pure glue, but also I think N=1 super glue satisfies, would be example, or in general pure glue with some adjoint matter. As soon as the number of matter fields, adjoint fields, is not too large, such that theory doesn't deconfine, that would be this class of theory. That would be such an example. Now, in theories like that, so again, one may consider, so in the strict planar limit, one may play the same game as one is playing with critical strings. Namely, one can consider dynamics on the wall sheet of infinitely long string. So again, at the similar, because 1 over NC plays the role of string coupling constant. So when 1 over NC, when NC goes to infinity, that dynamics on the wall sheet decouples from all the rest. And on one hand side, one still expects to find some features of TT bar like dynamics. So for instance, one expects to find Hagedorn behavior, which corresponds to deconfinement or center symmetry breaking in this theory. And also one expects to find this phase shift, geometric phase shift, because if one thinks about scattering of high energy degrees of freedom on the wall sheet, well, high energy degrees of freedom on the wall sheet, they're just partons. If the series is asymptotically free, they're just partons of underlying gauge theory. And so when one scatters two partons, then one forms this zigzag type configuration, because at high energy particle production, hard particle production is suppressed. And so one forms these zigzags, and these zigzags produce the same time delay, which is proportional to the collision energy, which one finds for critical strings. However, because the theory is non-critical now, so for instance, in pure glue, there are no additional massless degrees of freedom on the wall sheet. There are only two transverse modes. So that means that inevitably, there is inevitable particle production in these models. And well, which comes from this calculable one loop effect in Nambu-Goto theory, which is proportional to d minus 26. So often people say that TT bar deformation of free bosons always produces Nambu-Goto theory. Well, actually, it's not really. If my Nambu-Goto theory one means the theory of Poincare invariant string, then that's not true. Then a quantization of Nambu-Goto theory consistent with target space Poincare invariance corresponds to TT bar deformation only at d equal 26. Well, and d equals 3, another special case. I won't talk about that much, but at d equal 4, which is most physically interesting situation, TT bar deformation is not the same as Nambu-Goto theory, even though at the classical level of classical Lagrangian they agree. So in the wall sheet series, there is inevitable particle production. And so that suggests that by considering this set of examples, one actually will find like broader class of theories which also have this interesting UV behavior, but one doesn't expect them to be exactly solvable. And so that's one route along which one may just understanding this series. That's one way how one may approach constructing more examples of theories with TT bar like UV behavior. So that's that's motivation coming from TT bar side. So are there any questions, by the way, or on what I said so far? Also, just I wanted to make sure that people hear me because you can hear me, right? So I'm talking to. Hello?
Yeah, you hear me.
Yeah, okay, good. Okay, so, and to understand these kind of questions, we were considering even simpler, like probably the simplest possible setup, so not 4-dimensional gauge theory, but we're considering even simpler model, namely adjoint QCD in 1+1 dimensions. So it's theory with this action for G squared trace F minus squared plus, well, in the simplest case, it would be there will be single Majorana massive adjoint flavor. So this psi is Majorana adjoint, and well, simplification of this case compared to 4-dimensional pure glue, for instance, is that one can consider the regime when, so in 1+1 dimensions, G is dimension full coupling constant, has dimension mass. So one may work in the regime when mass of this fermion is much heavier than the string coupling scale. And one expects, so then there are no light degrees of freedom, and one expects in this case to be developed some kind of weak coupling expansion. So I will be working in this regime, but as before, so in order to be able to discuss Volsheet theory, like I will focus on the Volsheet theory, meaning I'm taking NC to infinity limit. So I work in the strict planar limit. And then just like in higher dimensions, one may, well, kind of physically, one may think about Volsheet theories by introducing, say, two non-dynamical fundamental, anti-fundamental fermions, so some non-dynamical sources, and then stretching them to infinity. Then there is a flux tube between them, and there are no propagating degrees of freedom coming from gauge fields in 1+1 dimensions, but thanks to the presence of adjoint fermions in the sector, in the theory, there will be fluctuations corresponding to inserting inside of this flux tube. I can insert adjoint fermions, and they can scatter, and in infinite at the limit of in the planar limit. So these kind of perturbations, they form unitary sector which decouples from the rest of the theory. And by the rest of the theory, I mean, for instance, there are also hadronic states which can be drawn, represented like this, or there are bound states of these adjoint quarks which describe infinite set of hadrons, bound state present in this model. But in the planar limit, they're all decoupled from each other, and the Volsheet dynamics corresponds to dynamics of this sector with infinitely long string. And one then can proceed in the standard way, namely one can fix, say, the gauge M1 equal to 0, fix spatial gauge, integrate out A0, and this way one arrives at the explicit expression for Hamiltonian describing these dynamics, and taking large NC limit, one gets explicit expression for Hamiltonian describing dynamics of this Volsheet sector. And with that expression, with this playing with this expression, then one can take the following limit. One can take the limit when I'm considering collision energies on the Volsheet much larger than the mass. So I'm taking ultratellistic limit, but I'm still taking also this limit. So everything is all energy scales are much larger than the string tension scale, the tension of the string scale, scale of string tension. And in this limit, if one stares at this Hamiltonian, then there are terms which, well, in the momentum space, there exhibits. So basically, what we're trying to do, we're trying to develop some kind of high energy expansion in this theory, which is not trivial, because even though the theory is naively weakly coupled at high energies, there is a string present, which is a like non-perturbable, like long, strong IR effect, and it exhibits itself in this Hamiltonian due to there are certain terms in this Hamiltonian which in the Fourier space looks singular. And so basically what we did, we picked up leading singularities in that Walsh Hamiltonian, which one gets that way, and the result is the following. So this singular part of the Hamiltonian, it first of all it corresponds to decoupled, describes set of decoupled sectors with different number of partons. So like different number of fermionic insertions inside the string. That number is fixed. So Hamiltonian, full Hamiltonian in this limit, in this relativistic limit I'm talking about, it can be, it becomes sum over subsectors with different number of partons. And this Hn is given by the following. So when one rewrites it in kind of not in the Fourier space, but in conventional in the position space, then it's n particle Hamiltonian of this following form. So it's I equal 1 to n, so the value of pi plus g squared over n over 4 pi sum over v qi minus qi plus 1. So there is a interactions. There's a potential which describes interaction between neighbors. So this ordering here is just corresponds to ordering, color ordering. So how these particles inserted in the flux tube, and this potential takes the potential between neighbors takes the following simple form: V is just equal Q plus absolute value of Q bar, which means that when the ordering of particles, like color ordering, is the same as ordering in space, then energy is 0. So when two quarks are located like that, that gives V equal to 0. On the other hand, when color ordering of neighbors is different from color ordering of the space ordering, then V is equal to 2Q. So in what follows, I will set this, I work in the units where string tension is set to 1. So for kind of obvious reasons, that's what this is what zigzag model, that's what we call zigzag model. So this is a model which describes dynamics of these zigzags. Well, according to kind of the logic which I outlined in the beginning, one might expect here that actually this model will actually correspond to exactly to TT bar deformation. So initially I said, well, when one talks about non-critical strings, then one doesn't get TT bar in general. But here the peculiarity of this model that these gluons which I have here, they're no massless gluons. There are these massive particles, and by considering this limit, when taking this order of limits, I kind of managed to suppress particle production, which is present in the series. It appears at high order in this high energy expansion, but there are reasons to expect that this leading high energy asymptotics will be really equivalent just to TT bar in the sense, well, we already see there is no particle production, there is no mixing between sectors with different number of particles, and well, at least it's plausible this potential, they can just solve it classically, they can for two-body problem. It's plausible that, well, this potential gives rise to correct TT bar time delay. So the expectation was that this theory which I wrote here, well, maybe it describes really something like n particle subsector of TT bar, massless TT bar deformed fermion. So that's essentially what I will try to explain now how it happens in the remaining part of the talk. So for now let's study this classical model. So the most part of my talk will be about classical dynamics of this model, which we understand completely now. So first of all, it's turns out to be quite interesting. So first of all, this model is Poincare invariant. It's a classical level, which is already non-trivial because, well, there is.
Excuse me, can I have a question?
Yes, sure.
So this N is number of these fermion particles.
Yeah, sorry, there is confusion. Yeah, so this N is different. Yeah, so I used two different
so,
N's.
Yeah,
so there's here it's NC, right? So N
you already
appears here.
Oh, there's NC.
No, NC is what appears here in the coupling, and C appears in the string coupling. But this N, that's the number. That's like let me call it N tilde. That's the number of particles, right?
So the summation contains the index N.
Right. I call it N tilde now, right? So.
So basically, the potential energy is a positive definite.
Yes.
So it seems that the total energy H, which is sum over this N tilde, seems dominated by large N tilde limit.
No, but here it's really this is different N tildes just correspond to different subsectors. So the full theory, the full theory describes this N tilde is just a number of partons.
That's right.
Which I introduced inside the Volt sheet.
Yes.
And so this is just a statement that in this leading order in the high energy approximation, the full theory with different number this describes all subsectors with different number of partons. It actually decouples into different sectors where until the fixed N tilde is a closed subsector of this theory. So the number of particles that doesn't change. And now I will just work on one of the subsectors. So I picked one of them, and I'm looking.
So you are not considering thermodynamics, for example.
No, I'm not. Yeah, I'm not. Well, I'm not considering thermodynamics here. No, I really want to understand just N particle subsector of this model. Yes, that's right. Well, once after that is understood, one can also, of course, go ahead and ask questions about thermodynamics. But so here I will be concerned just with dynamics in the sector with fixed number of particles. That's right. Okay, so first of all, well, one could have expected it from the way if we really how we obtained this theory, because we took high energy limit in relativistic theory. So one can expect that it will be relativistic invariance theory. But on the other hand, it's somewhat non-trivial because in general, well, there are few in between examples of interacting relativistic n-body systems. And actually, there is a statement called no interaction theorem, which holds in high dimensions, which says that it's impossible to construct interacting n-body systems with finite dimensional phase space. And that's classical reason why we need field theory when we talk about relativistic dynamics, even without going into quantum mechanics. Just if you want to describe relativistic dynamics in the canonical language, one needs infinite dimensional phase space. So, but 1 + 1 dimensions is special, and so well, actually, that's an example. It's essentially the only counterexample to the stable. Well, there's some other class, but that's the simplest set of counterexamples to the statement presented by this model. So that's already makes it interesting. And what I mean by Poincare invariance, so one can construct, like, can write explicitly the expression for the boost operator. So of this form, Qi pi plus 1/2 sum over I Qi plus 1 times this V of Qi minus Qi plus 1. And then it's straightforward to check that at the level of Poisson brackets, then one has Poincare algebra where P is the usual conserved momentum, P1 plus Pn, and Jp is equal to H, and Jh is equal to P. So this is n-body relativistic system, which is already interesting. And what I will prove to you now that actually it not only it's relativistic, but also it is well, strictly speaking, it's what's called maximally superintegrable, which means that there is it has the maximal possible number of independent conserved charges, meaning this is 2n minus 1. So if I have a 2n dimensional phase space, the maximal possible number is 2n minus 1, which means that every trajectory in the phase space is just fixed by fixing the values of the conserved quantities. Well, in particular, it's also there is a subset of those, n of those which are involution, so it's also Liouville integrable, but it's stronger than that. So yeah, let me sketch for you how this goes. I think, well, I really like this classical model, so I will spend some time on that. I think it's fun to study its dynamics. So, well, and that also shows that indeed this model looks like a, coming back to motivation coming from gauge theory. So this model looks like a promising starting point for developing perturbation theory. So kind of the idea was to start in this full Volschild Hamiltonian, identify the part which would be called like free one, but it's not free because we talk about like the dynamics inside the string. So like the free approximation is not a good zero-zod approximation, but still some like identify some h naught, and this h naught has a looks like a good starting point because it is maximally superintegrable. So then one wants to kind of understand this theory and start developing perturbation theory around that one to understand dynamics on the Volschild beyond this integrable approximation. But we're, I should say, far from there yet. But so let me first explain how classical integrability comes about. And to construct these charges, it's first of all, it's good to introduce the following. Let's see how I'm doing on time. The following notation. So I introduce. I treat kind of all variables, all phase space variables democratically. Oops, P2. So by capital Q's, I will call the just a set of P1, Q12 is Q1 minus Q2, etc. Then P2, Q23. So I introduce this string of variables, and then it's actually also naturally introduce string of signs, which corresponds to signs of all these variables. So it's S1, where S1 is just sign of P1, and then there is S12, S2, etc. Sn, and in addition, so there are this index, little index A, runs from 1 to 2 n minus 1, because I'm only looking here at the coordinate differences, because all dynamics depends only on differences of coordinates. So there is 1 degree of freedom which decouples trivially. And then if one also uses notation, introduces notation, kind of S0 is equal to S2n equal to -1, then in these variables, the equations of motion of this model, they take this simple form. QA dot is equal to SA minus 1 minus SA plus 1. So these are the Hamiltonian equations following from the system. So the first observation that one can construct, so for the system, first one can construct topological charge, meaning the piecewise constant function of it on a phase space, which nevertheless conserved, meaning that different like the phase space actually it consists of different regions, well, corresponding to different values of this topological charge, which kind of don't mix with each other under dynamics. And this topological charge, it takes somewhat peculiarly, it looks like the Ising-Hamiltonian of this. If one thinks about this series of signs as kind of spin variables, classical spin variables, then it's straightforward to check that as a consequence of these field equations, the corresponding, the quantity which looks like corresponding Ising-Hamiltonian is conserved. Well, it's really a simple calculation, and it has the following. Its meaning is the following. So first, one can look at what values it takes at early times and at late times. So at very early times, what we have in this model, we have a bunch of right moving particles. So there is a bunch of right movers on the left, and so there is, say, n r right movers, and then there is n l left movers on the right, which so this is how what one finds at t to minus infinity. Well, and correspondingly at t to plus infinity, one finds similar picture, but with right movers on the right and left movers on the left. So there is you have this string configuration, quark meet each other, form the zigzags, like zigzag, zigzag, zigzag through each other, and at the end they all go through each other. And if one looks in these asymptotic regions, then this conserved charge, it's just the same as the number of is a difference between number of left movers and the number of right movers. Well, and actually at intermediate times, so if one looks at generic intermediate moment of time, then the string configuration will well, it look something like this, where so there is this corners where some particles sit on the corners and some particles move in between, and at intermediate times, this quantity calculates also the difference between numbers of left movers and right movers, where the rule is the following. So first one doesn't count the corners, so particles at the corners don't count. And then the definition of whether particle is left moving or right moving, it's with respect to the wall sheet of a string. So for instance, for this particle, if it moves this way, it would be called, that would be right mover. However, for this particle, so because wall sheet goes this way, so if this particle goes this way, so that that would be a left mover, because it's kind of wall sheet made this zigzag here. So that's the geometrical meaning of this quantity, but in particular it tells us that as a result of the scattering, the number like asymptotic left movers and right movers stays constant. So, well, this is kind of this topological charge. Now the charges, actual charges I was talking when I was talking about this 2n-1 independent charges, those charges are not like, they're not piecewise constant functions, they're dynamical charges. They really distinguish different, not just regions in phase space, but different points in phase space. To find these charges, we made the following answer. So if you look at this field the equations of motions, right? So all solutions here, they will be piecewise linear functions of time, right? So because these are all like the first order equations, and the things on the right hand side, they are constants. It's essentially either 2 or -2 or 0. So all solutions here are piecewise linear functions of time. So it's natural to look. It was natural to look for conserved quantities, which are just piecewise linear functions of phase phase space variables. So one makes the following ansatz. In other words, one looks for conserved charges in the form equal to 1 to n minus 1 fa of s qa, where these coefficients they depend on the signs, and then they are just multiplied corresponding p's or delta q's. So in other words, in some sense, one may think about these conserved charges as kind of some kind of logical statements. So basically, if kind of this function depending on signs is just basically a statement. So if your configuration has this and this form, kind of you have zigzag here, zigzag there, then you should take this sum of q's. If it has some different forms, then it will be different sum of then you take different linear combination of q's. So kind of that's one way to think about these statements and these conserved charges. And then one calculates I dot, and one finds, well, there are two kinds of contributions. There is a contribution coming from like there's a smooth contribution coming from derivative hitting QAs. So there will be smooth part from derivative hitting Qs, and then there will be delta functional contribution coming from jumps in these coefficients when some of the signs flip. And these two contributions, these two separate contributions, they should cancel separately, just because, well, one is singular, another is not. So by imposing cancellation of singular delta functional contributions, one finds that these FAs, actually each FA should be a function of a single variable, which is TA. So this TA is the following. It's the same it's generalization of this Ising Hamiltonian for the full chain, but one just makes some summation for TA. One just sums the summation variable here. Sums not up to the full chain, but sums up to, it's a kind of partial Ising Hamiltonian when you sum over up to corresponding point in the spin chain. So, and that's the only way, one straightforward to check, that's the only way to satisfy this consideration of delta functional contribution into I dot. And then there is a single condition which comes from requiring now the smooth consideration of smooth part, and well, that condition can be, so kind of, it roughly speaking, it takes the form of like recursion relation between different FAs, and then one can construct 2n minus 2. It's a linear equation which allows to construct it has 2n minus 2 independent solutions. So I don't have time to go into detail, but so what if one looks now after these charges, there's a nice construction, but if I go there, I will never reach the quantum part of the story, so I'll skip that. But let me just tell you what these charges mean asymptotically. So asymptotically, they correspond to the following. So if I look at t to minus infinity, so as we already said, there is a bunch of left movers, and then there is a bunch of right movers, and so these 2n minus 2 charges and t minus infinity, they just reduce to momenta. Sorry, these are right movers. They reduce to momenta, individual momenta of these left movers and right movers, P1, and these are left movers, and the coordinate differences between these right movers and left movers. So the conservation, and at t plus infinity, again, there is right movers on the right, now left movers on the left. And these conserved charges again reduced to the same things. So the conservation implies kind of integrability of the model in the most basic sense, that of individual particles don't change as a result of this zigzagging or as a result of the scattering, and also the distances between particles don't change, which means that there is kind of universal time delay. Each of the particles, each left mover and each right mover experiences the same universal time delay. Well, as a result of this construction, one actually finds another quantity which is not an integral of motion. Is there a question? But one finds in the course of this construction, we found one more quantity which Natural called H tilde, which is not conserved, but which has constant Poisson bracket with the Hamiltonian, which means it's on the solution, it becomes just a linear function of time. And again, there is some somewhat complicated expression for this quantity, but in the asymptotic regions, it takes this form, QR minus QL minus PL. I'll explain momentarily what this is. QR minus QL plus PR, oops, T to minus infinity, T to plus infinity. So here QR, that's the position of the rightmost right mover. Q left is the position of Q leftmost left mover, and PL and PR is the total left moving and right moving momentum. So there is a linear, in time quantity which with this asymptotics. So it's kind of roughly speaking, at early times, it's the distance, it's this distance between left, as I said, between leftmost left mover and rightmost right mover. So clearly at early times it changes linearly with time, but then there is a quantity which keeps changing linearly with time through the subsequent evolution. And then one may construct quantity which, let's call it P tilde, which is the given by Poisson bracket between the boost generator and this H tilde. And then it's straightforward to check as a consequence of the of the algebra. Then actually this quantity P tilde, that's yet another conserved charge. So that's 2n minus 1's first conserved charge. But unlike all the previous ones, this one is not translationally invariant. So it's Poisson bracket with the total momentum is equal to 2. And again, in two asymptotics, it reduces to minus QL minus QR plus PL minus QL minus QR plus PR. That's T to minus infinity and T to plus infinity. Oops. And now by combining these three formulas, the fact that these three facts that H tilde changes linearly with time, and it takes this form asymptotically, and P tilde is a conserved quantity which takes this form asymptotically. From these formulas, one may now find also that algebraically one can determine time delay in this model, and one finds time delay, which is delta for left movers is just equal, as I said, is a consequence of conservations which we already have. It's the same for all left movers, and it's equal as a consequence of these formulas which I wrote here. It's just the total right moving momentum, and the for right movers it's the total left moving momentum. So in other words, at the classical level, this integrable model indeed describes TT bar scattering. So that corresponds to TT bar phase shift for massless massless particles. So that's at the classical level. This is TT bar time delay. Well, so that's the end of the classical story. So what about quantization? So in the remaining,
so before you going into there, your time delay delta TL is a sum over all the left moving particle time delay.
right? Yes. So this is PR P sub R. That's the sum, the total right moving momentum, and the P sub L. That's the total left moving momentum.
So can you find individual left particle time delay, for example?
No, this time delay is every left moving particle, because the time delays, yeah, they're all the same, right? So for every individual time delay is equal to this, and every individual time delay for it mover is equal to this. And that's exactly what happens for TT bar, massless TT bar scattering. Okay, so what about quantization? So, well, first of all, well, given that we have a like TT bar deformed series in many, like in some formulations and many quantities there, they come out one loop exact. And so here we have a classical integrable model which reproduces exact phase shift for quantum theory. So we like coinciding with the exact phase shift quantum theory. So one expects then there should be a quantization of this model such that phase deal that it really becomes also at the quantum level that phase shift becomes TT bar. However, one expects it to be subtle because, well, already so. And the reason one expects it to be subtle is that, well, already for, as we know very well, is already for pre-relativistic particles. Pre-relativistic particles, quantization is subtle in the sense that, say, position of a particle x bar is not a well-defined operator in a sense. Well, there is no naive causality, right? You can, of course, consistently quantize theory in the momentum space, and that corresponds to one particle subsector of relativistic theory. But if one tries to build kind of the position operator and try to interpret corresponding wave function as a wave function, one finds a causal propagation. Because that doesn't mean that theory of relativistic particle is inconsistent. One just needs to interpret it properly. So it answers, like it allows to calculate certain quantities, gives correct answers for certain quantities and not for others. So the same one expects to be here. So here it's kind of interacting version of that story. And well, in particular, as I said, so one should be careful in asking questions, but I would expect that like the answers to correctly posed questions about good observables, in particular about S matrix, should come out right. So that was kind of our initial expectation. So I'll skip. There were a couple of figures like illustrating this classical procedure of constructing integrals, but I was too optimistic about how fast I will be moving, so I'll skip that part. Okay, so and in the remaining time, I will talk about just two particles. So it turns out to be hard enough to quantize two particle subsector. So I will talk about n equal 2. So namely, I'm talking about this simple model, right? I'm talking about two particle theory with this Hamiltonian Q1 minus Q2 plus absolute value Q1 minus Q2. Okay, so the most naive thing one may want to do is then to say, okay, let's just impose canonical commutation relations. Qi J is equal to I delta Ij. Let's work in the coordinate representation and write just the conventional Schrödinger equation. So there is slightly non-conventional. So one needs to define operator absolute value of P, which is somewhat non-local, but that sounds like that's not a big deal. We know how defined this kind of operators, right? So it's from minus infinity to infinity, dq prime psi of q prime times principal value of q minus q prime squared. So we know what the Fourier transform of absolute value P. So by following this rule, one can try to then solve corresponding Schrödinger equation. And when one starts doing that, well, it turns out that procedure doesn't give good results. So that procedure is wrong. And there are several ways to see what goes wrong. So first of all, as you saw in the classical story, it was crucial. There was this piecewise, this was topological charge, and as was space was separated in the left-left, left-right, and right-right subsector. And it's easy to see that here in these quantizations, they're all mixed up. So one loses these subsectors. One may say, okay, maybe it just describes, and actually there is no left-left and right-right at all. One may say, okay, maybe those are kind of boring. There one just has free particles. So maybe this will describe left-right subsector. In the left-right subsector, one can just try to solve the results in Schrödinger equation. One cannot do it analytically, but it can be done numerically. One finds phase shift, modified phase shifts. So phase shift is not of the modified phase shift. It changes. So it doesn't correspond to TT bar. Well, maybe there was something wrong with the expectation. And probably the main reason is that if one follows this quantization and then tries to write the quantum version of the boost generator, then Lorentz algebra it's got broken at the quantum level. And so that's the real reason why we don't like this quantization. It doesn't preserve Poincare invariance of the model. Sorry, there was a question. So to understand what went wrong, so let's look at in more detail. Let's draw several snapshots of the classical phase space which we have. Now I will work now in the variables like capital P, which is P1 plus P2, and little p, which is P1 minus P2, and little q, which is Q1 minus Q2. So, and I will be drawing at different values of total at capital P, which is the total conserved momentum. I will be drawing the snapshot of the phase space in little pq coordinates. And so, for instance, at capital P smaller than 0, phase space looks, classical phase space looks this way. So there is there are two regions, and one region which was corresponding, this is left-left, so this is capital P over 2. This is minus capital P over 2. So there is this region which corresponds to left-left sector, and the rest is corresponds to left-right sector, and kind of the trajectories in phase space, they go this way. There are the scattering. So nothing happens in left-left sector. They're just momenta, like Hamiltonian in this cut, it just vanishes. It's trivial, and particles move that way. And then at P equals 0, at the total P equals 0, there one should cut away this region. So there is this line. It's not really part of the, well, that's where, because remember, the Hamiltonian which I have, it has these absolute values. So there are some singularities in the classical Hamiltonian, which are benign at the classical level because those singularities are never reached dynamically. But still, the singularities are there, and at P equals 0, so they on the at non-zero P, they correspond to the boundaries between these different sectors in the phase space. At P equals 0, it's just this line. So there is left-right sector, and at P positive, it's the same picture as here, but instead of left, one finds right here. So what I'm trying to say here, that really the physical phase space already at the classical level, the physical phase space of the system is not R4, but is R4, which is separated into subsectors. And the boundaries between subsectors, they should really be cut out. And already at the classical level, one can see that because the boost generator, classical boost generator, it's not defined on the full R4. Because it changes the value, total value of P, and so it would for instance, allow to go from P positive to P0 or to P negative, and that's only can be defined separately in each of the subsectors. And this boost generator is not defined on the boundaries, and this is the reason why the naive quantization of the system, which completely ignores this geometry, non-trivial geometry of phase space, when it breaks Lorentz invariance, because already at the classical level, if one ignores that fact, then Lorentz invariance is broken. So it looks very technical, because there are some commutators, one tries to track contact terms, but at the end there is a very simple geometrical reason why that quantization is anomalous, because it doesn't, it ignores the correct geometry of the phase space. And so the way to proceed is to, first of all, one needs to quantize in different subsectors, and one needs to introduce correct coordinates in each of the subsectors, which parameterize those subsectors and work in those coordinates. I'm already kind of running out of time. Probably I'll finish in a few minutes, so I'm almost done. And it turns out, well, maybe not surprisingly, that these coordinates, these classical integrals of motion, these 2n-1 integrals of motion, and quantity which depends linearly on time, those coordinates they provide, those quantities provide natural set of coordinates. Namely, they really provide a globally defined set of action variables for the system. So I will talk about only left-right subsector because that's the only interesting one. The left-right subsector, then kind of there is a canonical change of variables globally defined in the whole left-right subsector, which corresponds to going to those coordinates, where the Hamiltonian, so the system can be written in the following way. So these are capital P1, capital P2, capital Q1, capital Q2, which are essentially those conserved charges which I was talking before, which I constructed classically, and they are restricted. P1 is positive, P2 is negative, and total P is equal P1 plus P2, and H is equal to P1 minus P2. So in these coordinates, the system looks like really just system of two free massless particles. And kind of if one quantize, now one can kind of quantize in the momentum space, P1, P2, and there is a boost generator given Q1, P1 minus Q2, P2. So well, it looks like a system of free particles. However, well, one may ask, okay, where TT bar dynamics is coming from? Well, it's the same way as actually in the field, the full TT bar. One should recall that like physical coordinates are not these ones, but the ones which we started with. So in other words, one wants to, so one should look at the expression for physical Q, the difference, I will write that one, the difference between Q1, so Q1 little initial coordinates, Q1 minus Q2, it is, well, it's given by somewhat scary expression. It's Q minus P over 4 minus 1/2 Q minus P over 2, where capital Q is capital Q here is Q1 minus Q2. So it looks a little bit scary. It gets simpler in the P equals 0 in the rest frame. In the rest frame, it just takes this form. Q is equal to chat over 2 minus Q. Then, well, one can write by essentially what one can do, one can write, take this operator equation and put, so we quantized in the essentially when p equal to 0, then the only variable which is left is the total value of energy. So we quantizing the system already in the energy eigenstates. But to solve scattering problem, we want to calculate kind of scattering S matrix, which obtained by, like, one needs to go back to coordinate representation. By coordinate, we mean this physical coordinate, little q. So one needs to take this matrix equation, takes matrix that takes this matrix element, and then this equation. So I'll write the result, and then I'll finish. So q. So if one calls this psi h of q, then one gets from here, one gets this expression h over 2 psi h of q plus 2 over pi integral from 0 to infinity dh1 psi h1 p of h1 minus h squared. So there is this equation which, well, it looks a little bit like Schrödinger equation, but it's not a Schrödinger equation, because it's Schrödinger equation is equation for eigenvalues of Hamiltonian. This is equation for eigenvalues. So I quantizing the theory directly by building by fiat the basis of eigenfunctions of Hamiltonian. So this equation instead, it's equation eigenfunction equation for this operator q, for coordinate operator. But still, one can solve this equation, and by solving this equation, because this quantity has still, it's the same matrix element which one calculates when solves Schrödinger equation. So one can extract from the solution, one can extract S matrix, and by solving this equation, one finds the correct T bar S matrix. So one finds that in the region q going to minus infinity, psi h, this psi h, there is a e to the iq h times e to the h squared plus e to minus iqh minus I h squared. So one reproduces from this quantization, one reproduces in the rest frame, reproduces the correct T bar S matrix. So there's a very last thing which I will say, but that's the thing which we're confused now for several months already. So we did it quite long time ago. So we wanted to make sure that the problem with initial quantization was Lorentz invariant. So this procedure which I'm following here is far from being manifestly Lorentz invariant. So we kind of try to repeat the same story in the frame with non-zero total p. And what we're finding is I'm still confused about that. Namely, we're finding that when one turns on non-zero p, that we find the correct expression for the relativistic expression for the phase shift. So this h squared there, it gets corrected into correct h squared minus p squared combination. So at face value, it looks like we're getting correct S matrix. But in addition to that, we're finding that these wave functions, well, what's somewhat strange, that the wave functions which we find here, they not what one would expect, but they have some extra phase factor which goes like this, and well, and there is e to minus I p q here, and well, that's basically our current status. So well, I think, well, we don't have good interpretation for this, so it's something yet to be understood. Well, I think it's a technicality, but well, we spent already quite some time on that, and that's the puzzle which stays. But at least in the rest frame, this quantization does reproduce T bar answer, and reproduces in the way one expects in the kind of T bar like theory. Namely, really, the physics is the same. The physics is that you redefine what you call your like you have a free theory, but you're using dynamical coordinates to define physical observables there, and that's how this TT bar phase shift comes about here. Yeah, I think I ran out of my time, so let me stop here, and thanks again for inviting me.
Probably. Yeah. Any questions? Any question?
Yeah, can you hear me?
Yes.
Yeah. Can you explain what is the relation to these folded strings that were studied like 20 or 30 years ago? I saw you had a comment on this in your paper, but you said they are closely related, and then you somehow said that one of them is like a short distance limit and the other a long distance limit. But do you have a precise understanding what is the relation? I mean, in the end, there should be presumably only be one type of consistent folded equals zigzag type string.
Yeah, but you mean these papers, which like in 70s?
Yeah, there was this Hansen et al. And so on.
Right.
Also,
yeah.
Even Polyakov wrote a paper at some point. I mean, Sasha Polyakov wrote a paper on folded strings at some point.
Well, that one I'm not aware of, but yeah. So here the relation is very simple. So basically, those papers studied, essentially the different sector. So as I said in the full QCD here, there is a sector which we are focusing on, which is a sector when you have infinitely long string with these insertions. But there are also sector which describe mesons. And so that's the simplest one, but in principle, one can also consider mesons with larger number of partons. So that system studied in 70s, yeah, that was describing these guys, and we are talking here.
Yeah. Well, okay, I understand. And then if now use, that's right. That's exactly what struck me when I read this, because you were talking about sectors. But then does this mean that your model itself is only like a part of an even bigger model?
Well, yeah, it's just like for critical strings, right? So because this model is obtained as taking strict planar limit of the full gauge theory. So a strict planar limit is the same as taking GS to zero limit. So, and in that limit, all these sectors, they decouple from each other. But at finite and C, they would be mixing. So at finite and C, there would be non-trivial scattering which would correspond to space-time scattering in string theory. But here I'm studying really like free limit of string theory. But one thing which is important to realize that free limit of string theory is not the same as free limit from the worldsheet point of view. Even in the limit.
So if you switch on GS again, somehow there might be a bigger, I mean, should be a bigger model, which
right, yeah.
Already the sectors start communicating and so on.
Right.
Okay.
So there are several limits which I'm taking here. In the gauge theory language, yes, so I'm taking G squared and C to infinity. Yeah, but even after that is so, and that's what controls this communication between different sectors. But even after one takes that, still the theory which describes a single sector, it's not integrable, it's not solvable. So we're trying to understand that theory, and then we're taking this additional kinematical limit, we're taking high energy limit in that sector, and then we get in this TT bar solvable TT bar dynamics there. But so then the next step would be, before going to non-planar limit, the next step would be just still to understand the single sector beyond this infinite momentum integrable approximation. And that's on its own very, very non-trivial and very hard. Yeah.
Okay, thank you very much.
Mm-hmm.
Any other questions? Okay, if not, let's thank speaker Dubovsky.
The morning session is online part is over.